Hello, today we will be doing chapter number 11, Intermolecular Forces. This particular chapter is actually the result of the ending for chapter 10, where we saw that real gases do not behave as expected under the ideal gas conditions, and there are two different conditions whereby the behavior varies. And so now this van der Waals forces that are there become very, very important when we are considering the liquid and solid phases that are there. So of the three matters, gases has been done as being independent and move separately without any force of attraction being acted upon them. So now we have to ask the question, what happens when there are intermolecular forces playing on a molecule? And these intermolecular forces are different from intramolecular forces. And so we are going to now study how these intermolecular forces are going to affect the properties of compounds, elements, and different materials that are there. And I'd like to share my screen with you so that we can start going through it. Please remember, at the end of each particular slide that I am showing you, there are some self-study questions. Do take time to go through it so that you are sure about the understanding of the concepts, because understanding concepts helps you as you go further along why certain items behave as they do and what are the reasons for that. So in this particular unit, which is the first part of chapter number 11, titled as Intermolecular Forces, basically deals with the introduction, definition, impacts of states on states of matter, intermolecular and intramolecular forces, types of IMF forces and their origins, and effects on the physical property. So that is the basic objectives for this particular chapter, first part of the unit that I'm going to show you. And then we will go on to the second and third units and complete this particular chapter. Now, if you were to keep the states of matter, we know that there is a gaseous nitrogen, liquid nitrogen, and it will, so you can see, so nitrogen is a gas and it liquefies. We know that because we can get the cylinders of nitrogen. And in the liquid phase, the nitrogen molecules are close to one another. But in the gaseous phase, they are far apart. And the same thing with what happens when we have liquid benzene. And then, if it is cooled to its freezing point, you get a solid benzene, and how the figure shows how closely they are packed together in the solid state that is there. So the intermolecular forces impact on physical properties. So basically, the question is, what is the impact of intermolecular forces on physical properties? Intermolecular forces are involved in differences in the boiling melting point of solids. Energy changes required for phase change to convert from solid to liquid, liquid to vapor, determine the solubility of gases, liquids, and solids in various solvents, and it is crucial in determining the structure of biologically important molecules such as DNA and proteins. Next, what is the difference between intermolecular forces and intramolecular forces? Remember, intramolecular forces are bonds. They give stability to the molecule, as well as they can be either ionic or covalent. Intermolecular forces are forces between particles, and they are considered as bulk properties, freezing point, boiling point, etc. Now, one exercise that I would like you all to do is, before you continue with the slide, is draw the representations for the following: a dipole, a polar molecule showing the dipoles, an ion, a water molecule, a cation, an anion, and a cation in water. Now, why am I asking you to do this? Because this, if you remember your chapter 8 in General Chemistry 101, where we drew the geometry of the molecules and studied the various properties of each of the molecules that we had drawn in terms of bond angle, bond geometry, electron pair geometry, molecular geometry, and the bond order, then this is a way to recap and make sure that you understand what we are talking about, and you get the gist of it. Now, intermolecular forces collectively together are called as the van der Waals forces. And the van der Waals forces first came into your preview is at the end of chapter 10, ideal gas behavior and the real gas behavior, how to explain the real gas behavior. Now here, what are the various forces and what is their energy kilojoules per mole, designated as in energy or strength is designated in kilojoules per mole, and the characteristics of it. The first is the ion dipole. It is a moderate force, and it is between 10 and 50 kilojoules per mole. It occurs between ions and polar solvents. Dipole is a weak intermolecular force, has a strength between 3 and 4 kilojoules per mole, and occurs between polar molecules. The London dispersion force, or LDF, is weak, and it ranges between 1 to 10 kilojoules per mole, occurs between all molecules. Strength will depend upon the size and polarizability of the molecule. And lastly, the hydrogen bond, which is moderate, ranging between 10 and 40 kilojoules per mole, occurs between molecules which contain OH, NH, and FH bonds. Now, covalent bonding forces for comparison of magnitude. Now, when you compare the intermolecular forces with that of a covalent bond in any molecule, for example, the figure that is shown, we see that the C double bond C is 610 kilojoules per mole. The CC bond is 346 kilojoules per mole, whereas the triple bond is 887 kilojoules per mole, and the CH bond is 433 kilojoules per mole, showing that the bonding forces are much more stronger than the intermolecular forces. The covalent bonding forces for comparison in terms of magnitude, we see that the distance between the hydrogen and chlorine molecule, that is the covalent bond, is strong, HCl, and the kilojoules required is 432 kilojoules. The intermolecular forces, because Cl has a slight electronegativity and it is negatively charged, so it attracts the hydrogen molecule, a part of the HCl molecule. It is a weak attraction forces. And so intermolecular forces are much weaker than the bonds that make up the compounds. The types of intermolecular forces between neutral atoms and molecules are London dispersion forces, dipole-dipole, and dipole-induced dipole, and H bonding. These are the various types of forces, intermolecular forces, which we collectively call as the van der Waals forces. In the forces that we study, another force is the ionic bond force that is very strong, and it is governed by the Coulomb's law. And it is assigned as the charge, the attraction of the charge on the positive and negative ions. And N plus is the charge on the positive and negative ions, and E minus is the charge on the electron. And the attractive force is given as equal to minus K, N plus E minus times N minus E divided by the square of the distance between the ions. Greater the charge, greater the force of attraction, greater the distance, weaker the force of attraction. These are strong forces that results in salts having high melting temperatures. H2O MP is 0 degrees. NaCl MPO melting point is 800 degrees Celsius, whereas MgO, which has a +2 charge, is 2800 degrees Celsius. Ions and molecules with permanent dipoles. We have studied this previously by introducing the solvation energy, delta H. Higher the negative, the exothermic value for the delta H, then the stronger the attraction is between the molecules. And that is because the molecules surround the water. And this is a figurative description of the ions and permanent dipoles. Now, water has a permanent dipole, as you can see on the extreme right. And the dipole exists, the negative charge exists on oxygen, and the positive charge exists on the hydrogen atom. And we have two lone pair electrons on it. And the polar nature of water provides for attractive forces between ions and water. This is a result of the solvation process when an ion is surrounded by a polar solvent molecule. Solvation of ions. When a cation exists in solution, it is surrounded by the negative dipole ends of the water molecule. When an ion exists in solution, it is surrounded by the positive dipole ends of water molecules. The energy required for this process is called as the enthalpy of hydration because water is used. If any other solvent is considered, then the energy for the process would be called as the enthalpy of solvation. And here is a measure of the ion dipole forces for different cations from the group 1 element. The cation is lithium, sodium, potassium, rubidium, and cesium. And as you can see, as you go down the periodic group 1, the size of the atom increases, and therefore we see that the enthalpy of hydration in kilojoules per mole decreases as we come from lithium to cesium, leading to the conclusion that as the size of the ion increases, the exothermicity of the process decreases. This is due to the weaker ion dipole forces. And we can see also how the size and the charge affects the hydration of ions, cations. So we see potassium has a distance. The distance between is the radius of the potassium ion is 133, and the delta H of hydration is negative 321. Lithium ion has only a radius of 78 picometers. The enthalpy of hydration is negative 515 kilojoules per mole. Now, magnesium ion is very close to the magnesium plus 2 ion, the radius is very much closer to the lithium ion, as you can see, because its radius is 79 picometers. And look at the effect of the cation plus loss of 2 electrons gives on the enthalpy of hydration. It becomes negative 1922 kilojoules per mole. Increasing force of attraction, more exothermic enthalpy of hydration. And this also depicts your enthalpy of hydration between different types of ions in the same group, or in group 1A and 2A. Magnesium is charged plus 2, and it is almost the same size as lithium at 79 picometers. Sodium is larger than that, and its size is larger, and it shows. And as we go along, the anhydration decreases as we go down the period because of the weak attractive forces that exist. The attraction between ions and permanent dipole. Once again, a repeat, water is highly polar and can interact with positive ions to give the hydrated ions in water, as shown. Now, the molecular polarity. Now, this goes back to what we studied in chapter 8, and that is molecular geometry. If the molecular geometry is linear, then both atoms the same, outer atoms the same for linear triatomic structure. Trigonal planar, all bonding groups are the same. Tetrahedral, all bonding groups are the same. Trigonal bipyramidal, all bonding groups are the same on both. Axial groups the same, and the 3 equatorial groups the same. Octahedral, they're same on this. All the groups are the same and are trans to one another the same. Any deviations from this nonpolar molecular geometry will give you a polar molecule. And this is very simple to understand, because you can see that as soon as a lone pair electron comes, we already discussed in chapter 8 that the molecule will be polar. So dipole forces bind molecules having permanent dipoles to one another. And you can see that the positive end of one molecule attracts the negative end of the other molecule. And so we can see dipole forces. When we compare it between molecules of comparable molar mass, we see that almost only this dipole interaction is only present in polar molecules. And when we compare them, C3H8, that is propane, has a molecular weight of 44, and its boiling point is 231. Its dipole is 0.1. Then acetaldehyde, CH3CHO, 44, again boiling point 294, 2.7, and methyl triamine, methyl cyanide is 41, 355, and 3.9. The mu is the bond dipole, which is a measurement of a polarity of a bond in a molecule. So when we compare the dipole forces between elements and compounds from group neutral molecules, hydrides and halo compounds, we see that nitrogen is 28, carbon monoxide is 28. So we see that the boiling point for nitrogen is 196 degrees Celsius. For that, for carbon monoxide is negative 192. The the enthalpy of vaporization is 6.04. Then we come down to silane, SiH432, boiling point 112. We say that the delta H of vaporization is 12.10 kilojoules. And so as we go along and down, we see that you can see the enthalpy of vaporization gradually increases. And when we compare it, now, when we compare, silane is from group 4, phosphorus is from group 3, carbon, nitrogen 4, nitrogen is group 5. And so you can see the variation of the enthalpy of vaporization as the molar mass increases. We can see that even though they are comparatively same, GeH4 is 77, ASH3 arsenic hydride is 78. The boiling point is negative 62. And the heat of vaporization is 16.69, whereas for germanium, silane, germanium hydride is 14.06. And for silane, it is 12.10. And for the halo compounds, bromine, the molecular mass is 160. The boiling point is 59. The enthalpy of vaporization is 29.96. And for ICl halo compound, is 162 is the molar mass and 97 is the boiling point. There is no heat of vaporization measured for it. So if you look at what is the effect of polarity on boiling points of molecules having similar molar masses, we see that compound, if we compare it, what we see is that we have a nonpolar compound, CH3, CH2, CH3, 44.1. The dipole moment is 0.1. The boiling point is 231. Ether, CH3, O, CH3 is 46.07. The dipole is 1.3, 248. Methyl chloride, 40.49, 1.9. And we have 249. And CH3CN, methyl cyanide, is 41.06, is the molar mass 3.9 as the dipole moment and 355. We can see that as the polarity for a given set of molecules with similar molar masses increases, the boiling point seems to increase. So generally we can say that if you want to find out what is the effect on the boiling point, look at the molecule to check out whether there is a dipole moment on the molecule, and then you can describe it as being that it would have a higher boiling point. Now, hydrogen bonding. There are 3 slides continuing with this hydrogen bonding, and I want to go through each. First of all, the hydrogen bonding is a special form of a dipole-dipole attraction which enhances the dipole-dipole attraction. So hydrogen bond, as its name implies, is between hydrogen and another atom that is there. The second atom can be nitrogen, oxygen, or fluorine. So these 3 atoms are highly electronegative, and H bonding is strongest when X and Y are H and O or F. So depending upon these, and remember, it is between hydrogen and the 3 atoms that are there. The water molecule network with one another. H bonding in water brings out a network of interaction which explains phenomena such as capillary action, surface tension, and flotation of ice. Next, the hydrogen bonding forms when atoms are small, they have high electronegativity, and they contain a lone pair of electrons. The atoms are generally forming hydrogen bonding are nitrogen, oxygen, and fluorine. The strength of the hydrogen bonding ranges between 4 to 25 kilojoules per mole. Boiling points of hydrides. You can see that where will H2C be and CH4 be? So basically, this is a plot of temperature versus molar mass, and you can see the effect of hydrogen bonding, that when the hydrogen bonding is very, very strong, the boiling point goes up very high. Whereas for the other elements in the same group, like oxygen, sulfur, selenium, tellurium, there is a very gradual increase with sulfur, H2S, having the lowest boiling point as compared to the others, so that we can say that the hydrogen bonding over here is not very high. Same thing when we go methane, selene, so carbon, CH4 is called as methane, CiH4 is called as selene, GeH4, germanium tetrahydride, and tin tetrahydride. You can see how the molar mass affects the boiling point of the given substance. And then the boiling points of different hydrides, like from, we have group 2, we have from group 4, 5, 6, and 7. So we see that group 4 is CH4. Group 5 is ammonia, NH3. 5. Group 6 is H2O, and group 7 is HF. And you can see how the hydrides, the boiling point of hydrides, vary with temperature and the period. And we see that water, again, because of its hydrogen bonding, has very high, comparatively very high boiling point as compared to HF and the remaining 3 periods compounds that are there. But once we see that in group 5 and the halogen compounds, they're almost gradually increasing. The boiling point of some simple hydrogen compounds, containing compounds are shown. Notice that water has an initially high BP for its molecular weight, and all are shown in terms of the molecular weight, because 18 is the molecular weight of water, 20 is for HF, 17 is for ammonia, NH3, and 16 is for CH4. Now, there are some self-check questions. Make sure that you do them. So basically, we have gone and discussed what are the types of bonding that is there. And so next, we'll go into depth how these bonds are formed in Unit 2 for this particular chapter.